This is a short video that will help explain the logic of hypothesis testing and also help you do the hypothesis test in the assignment for this week. In the general hypothesis testing situation, a sample is selected from the population. A treatment is administered to the sample, and the people in the sample are then measured. If the sample mean is noticeably different from the original population mean, we have evidence that the treatment had an effect. The evidence is significant because we've established that it's not due to mere chance. As I mentioned in the last class, there's two kinds of test, a two-tailed test or a one-tailed test. So let's first do the two-tailed test with this research question. What is the effect of prenatal alcohol on birth weight? We want to determine whether drinking alcohol while pregnant can cause birth defects. Low birth weight and retarded growth are two such defects that have been established in various studies. So first we'll select a random sample of 16 pregnant rats. The mother rats are given a daily dosage of alcohol. At birth, we're going to select one newborn rat from each mother to form another new sample. So the sample we're concerned about is the baby rats. And the average birth rate for the sample baby rats is M equals 15 grams. Now we want to compare that sample with the general population of rats. It's known that the average birth weight of regular newborn rats not exposed to alcohol is mu, which is our population, equals 18 grams. And the distribution of weights is normal, so we have a normal distribution with a standard deviation for the population equaling 4. So you've been given the sample mean, the population mean, and the population standard deviation. A word about the alpha level. Whereas in calculating the confidence interval, we're dealing with the 95 or 99% majority of the normal distribution. When we're hypothesis testing, we're dealing with an alpha level, which is that 5% or 1% that is very unlikely to occur. And that's why we're always focusing on the tail or both tails of the normal distribution. Both tails if it's a two-tailed test, one tail if the problem specifies the direction you're looking for. So let's go back to our sample problem. The first step in hypothesis testing is to state your hypotheses. Our null hypothesis here is that exposure to alcohol has no effect on birth weight. The alternative hypothesis is that alcohol exposure does affect birth weight. And we're going to use an alpha level of 0.05. In step 2, we're going to locate the critical region. We're going to do that by calculating the standard error of the mean. We're going to divide the standard deviation of the population by the square root of n. The population standard deviation is 4, and the number of individual rats in our sample of baby rats is 16, so it's going to be 4 divided by the square root of 16. 4 divided by 4 equals 1 divided by 1 equals 1. We know that for a normal distribution, the z-score plus or minus 1.96 separates 95% of the distribution from the extreme 5%. So we're going to have 0.025 in each tail. So what we've done is identified the sample means that have a high probability of occurring and those that are very unlikely to occur. And those that are very unlikely to occur are those that are going to fall in the critical region, and that's called a significant result. And it's not due to chance, or it's not random. Next step is to convert the sample mean to a z-score. Z equals the sample mean minus the population mean divided by the standard error of the mean. That equals 15 minus 18 divided by 1 equals a negative 3 divided by 1 equals a negative 3 for your z-score. Now, in step 4, we make a decision. Do we reject or fail to reject the null hypothesis? Since negative 3.00 is beyond our boundary of negative 0.196, our sample mean is located in the critical region. This outcome is very unlikely if the null hypothesis is true. Therefore, we reject the null hypothesis and conclude that alcohol does have a significant effect on birth weight. So you can see the math is very simple. The key is actually at the end in the interpretation. Okay, that was the two-tailed test. Now let's do a one-tailed or directional test. Food supplements like blueberries that are high in antioxidants have been shown to reduce and reverse age-related decline in cognitive performance for rats. So I'll eat a lot of blueberries over the next 25 years of my life. We want to determine if the same is true for humans. We select a sample of 25 adults, all over 65, thank God I'm not in that yet, and we give each a daily dose of blueberry supplement for 6 months. Cognitive performance for adults over 65 using standardized neuropsychological tests have shown that a population mean score of 80, population mean, with a standard deviation for the population equaling 20. For our sample, the sample mean equals 87. We expect that the supplement use increases test scores and that it will improve cognitive performance. Step 1, state your hypothesis. The null hypothesis is that there is no increase or difference in cognitive performance scores by virtue of taking the blueberries. The alternative hypothesis is that there is an increase in test scores. And that means we are predicting a positive or increase in the scores in one direction. So that's what makes this a one-tailed test. Again, we'll select alpha at 0.05. We locate the critical region. We assume that the distribution of sample means of n equals 25 for this population is a normal distribution. We'll calculate the standard error of the mean, 20, divided by the square root of 25 equals 4. If you were to diagram the normal distribution, this is what we're looking for. We're looking for something in that 0.05 area. If it's in the other area or the greater area of the normal distribution, we're going to fail to reject. Use the unit normal table. Look for a z-score of 0.05 and or 0.049. And look in column C, because column C is that proportion of in the tail of the normal distribution. The corresponding z-score for 0.05 Next, in step 3, we've got to get our z-value. So z is going to equal 87 minus 80 divided by 4, or 7 divided by 4 equals 1.75. Step 4, we make our decision. Since 1.75 is in the critical division because it is greater than 1.65, the outcome is very unlikely if the negative or the null hypothesis were true. Therefore, we reject the null hypothesis and accept the alternative hypothesis. And we conclude that the supplement does produce a significant increase in test scores. We can use another test called Cohen's d to determine how substantial an effect is significant. A d of 0.02 is a small effect, d of in the range of 0.05 a medium effect, and 0.08 is a large effect. Calculating Cohen's d is very easy. You simply determine the difference between the sample mean and the population mean. M capital M minus mu, and divide that by the population standard deviation. That's all there is to it. It's identifying whether it's a one-tailed or two-tailed test situation, and the rest of the steps are easy. The math is very easy. But if you have any questions, please do not hesitate to contact me.